Hello everybody. In this video I am going to be presenting simple analysis of a system of nonlinear ordinary differential equation, which is commonly used in what ecological modeling, and the name of this model is called Lotka-Volterra equations, and I'm going to be solving the equation in MATLAB computational platform. Okay, so I will be turning off my video camera because I don't want to set my eyes on the camera for too long. Okay, so Volterra equations, as can be seen from the name, I want to believe is the name of two scientists. Yeah, so we have Volterra. Okay, Volterra equation. Let me see if I can change the color. All right, so the Volterra equations were developed they were developed to describe the dynamics of biological systems. The dynamics of biological systems, and it's actually a system of nonlinear ordinary differential equations. Okay, it's a system of nonlinear ordinary differential equation, and it's kind of a more general version of the popular Kolmogorov model in modeling. Okay, now the equation focuses only on what? Predator-prey interaction. I need to highlight that. Excuse me. I need an highlighter. Okay. Cool. So it focuses on what? I need to highlight this. Okay. It focuses on predator-prey interaction, like interaction between, for instance, rabbits and foxes. Okay. And it ignores some factors like disease. It ignores competition. It ignores mutualism, which were included in the Kolmogorov model. Okay, we're saying here that Volterra model is a special kind of Kolmogorov model. But the Kolmogorov model itself have the following assumption: inclusion of competition, disease in the model, and mutualism. Okay, but Volterra was made to be very simple. So because of that, Volterra model have the following assumption: there is no shortage of food for the prey population. So in this instance, your rabbits, they have something to eat all the time, for instance, and the quantity of food available to the prey is directly proportional to the size of the prey population. But that may not always be the case. Also, the third assumption is that the rate of change of population is directly proportional to its size. Look at that. The rate of change of population is directly proportional to its size, and the environment is constant, and the genetic adaptation is assumed to be what? Negligible in that model. Also, another funny assumption is that the bad guy, the predators, will never stop eating. They will never stop eating. For instance, if you have rabbit and foxes, foxes will always be eating up those rabbits. So that's the assumption of Lotka Volterra model. Okay, and you can see the model clearly up here. Okay, can see the model clearly up here. Now I'm going to explain some things here. It's a system of it's a nonlinear system. It's a nonlinear system of two variables, okay, x and y. So it's a system of nonlinear ordinary differential equation, which you can call it 2 by 2, okay. Now in this model now, x is assumed to be the number of prey, y is the number or the population of the predators. So x and y are quantitative variables, okay. X and y are what? X and y are quantitative variables, okay. I see that right there. And the x, the t, is given as alpha x minus beta xy. In other words, the rates of change of prey population, x is the prey, so the population is growing at the rate of alpha. Alpha is a constant. The rate of growth of the prey population, okay. Also, the prey, when prey interacts with predators, like you have here, look at that. That's the rate of deaths for the prey. It's negative beta xy. Xy is the interaction between the predators and the prey. Okay? So in the first equation here, you see that the prey has some trouble there. And the second equation is the rate of change of predators population. Okay? Now, predator will only grow as long as it is interacting with the prey. You can see that xy is the product. Whenever you have two quantities multiplied together, or when you have your dependent variable in the model being raised to power that is not 1, like the x dt equals x squared, the y dt equals y squared, or the x dy, you have xy, which is a product of two variables, then it becomes nonlinear. So the rate of growth for predators population is delta, this delta here, and that is why you have it here. See, because the predators can only increase as long as they are eating up the prey. And also we assume the rate of deaths for the predators as gamma. Now the gamma may be due to natural occurrence like sickness, like disease, or like any other thing. Okay, that is so nobody can live forever. The foxes themselves will have to die, and the rabbits also are being killed by the foxes. So that is a simple model. I'm going to be running. I'm solving everything in MATLAB. Okay. Once again, look at the model. It's a what? System of ordinary. It's a system of nonlinear ODE in two variables. The variables x is what? Prey, Y is predators. Okay? Now let's go to MATLAB and solve that. Cool. Okay, I'm in MATLAB environment right now, and I'm going to create a new file. I'm going to call it edit. I'm going to open a new file. Now, I've shown you the first thing I want to do here is to build the ODE function. Let me call it the X, the T, or let me call it the Y, the T, okay, equals ODE. Let me call it ODE. Let me call it ODE3. I can call it ODE4. I can call it ODE5. I might have added some function called ODE1 and 2 there. So let me call it ODE3, for instance. I'm calling it my ODE, or let me call it my ODE. Okay? And your ODE has to be a function of time and Y. Okay? This is what spatial variable, which has to be a vector, right? So in this instance, your Y has to be what? A vector of what? Y1, maybe for prey, and Y2 for predators. Okay? So this, your Y1, for instance, might be representing your prey, and your Y2, your predator, X and Y. Okay? So that is that. And when I solve this model, okay, it should be returning Y1 and Y2. So initially, I'm going to assign value 0. So assumes 0 initially, right? Just for, you can assume anything. You can put 1, 1 here if you like. You can put 1, 1 here if you like. You can put 1, 1. And you can put 0, 0. So, because I need to put my solution in that square bracket, okay, just to hold some default values. Okay, look at that. And the next thing is what? Supply the model parameters. So, i.e., rate of growth and depths in the model. Okay, that is very important. Okay, so let me call it alpha. Let me, I'm assuming 0.4 for the alpha, which I believe is the growth rate for the prey. And I'm assuming beta, according to the model, to be 0.4. And you can always go back to the video and check. And delta is 0.09. And I'm assuming gamma to be 2.0. That is just the rate of growth and death. So I can't remember precisely, but if you go back in this video, you can check what we have. All right, and the next thing after supplying the rate is to what? Solve the model divided t, the first component of the solution. Remember, this is a 2 by 2 system of ordinary differential equation. So when you solve it, you must have 2 vectors. 2 fields, 2 columns. 2 columns of solution y1 and y2. So the first solution. And remember, when you solve ODE, you are actually integrating. When you represent ODE, it's actually a derivatives. Okay, it's derivatives. So dy dt, now this dy dt 1, this first component, it's your dx dt in the original model. So alpha times y of 1 and minus, according to the model, beta times y of 2. Now this is our prey. This is our prey. I think I'm missing one here. Times y of 1. Remember, your prey we have, we die when there is foxes. So when there is interaction between y1 and y2, that is when your prey will die. That is why you have negative here. Okay. And the second component of the derivative, the y dt of 2. Now, if you don't have line 9, you cannot have line 12 and 13. Okay. Because this is assuming this is already known. Okay. First component, second component. Now, the compiler will be asking you where is the original value for your dy dt for you to be able to get dy dt 1 and dy dt of 2. Okay, so the second component is delta times y of 1 times y of 2. Remember, this is the growth rate for the predators. So as long as the predator is interacting with the prey, there will be what? Growth rate for the predators, like growth rate for the foxes. And we said in that model, the rate of death for the predator, which can be due to natural occurrence, is gamma. That's gamma times y of 2. Okay, now this is the predator. Okay, now you define the model and then you end it. You end it right there. You end it right there. You end it right there. So once again, look at it. I'm just defining the model. If you have 3x3 model, if you have 3x3 equation, all you have to do is to keep adding like dy dt of 3. Okay, and then you have to get initial condition for the third component, but we just have 2, x and y, prey and predators. That's all we've got. Okay, so and then I'm going to create a calling function. Let me call it run my ODE. Okay, let me put an end to it there. See, I'm modularizing my function. Let me save this as run my ODE. Okay, now if you still remember, look at line 13. My ODE is a function of time and a spatial component y, which is of course a vector in this instance. Vector representing the what? Population for the prey and population for the predators. Okay, so you solve it over time. Initial time, let's start from 0. Okay, and call this initial time, and then t final, call it let me have 40 final time. See that? And then remember, when you are solving nonlinear ordinary differential equation in numerical analysis, you have to assume initial condition. So initial condition for vector y, let's say we have 10, 10, 10, 10. Now, you have to be careful that here you must use a semicolon, because in MATLAB, semicolon is separate from using comma. See, look at that. It's a vector. It's a column vector. Or if you use comma, right here, you are going to get, I think, horizontal vector. See that? So you have to be careful of the dimension. So also, if you don't use anything there, just put space. MATLAB assumes horizontal. But if you want to have column vector, you must have semicolon between them. So you've got to use what? Semicolon. So let me just write a comment there. Column vector needed here. Okay. Now, that's initial condition. Initial condition for, let's say, prey and predator. And we need a column vector. We need a column vector there. All right. Okay. And the next thing is, I have supplied the time and the initial condition. That is very, very important. Then next thing is to call the solver. And when you call the solver, you can tell the solver to give you the time point and the what? Solution y. Don't put y not. It has to be y, okay? Come on. So, if you don't want time to show, you still have time, okay? You have time because you're going to plot the component of y or against time. So remember, your y has two components, y1 and y2. So you call OD45 solver, and then you call the function my ODE. So this add symbol is called function undo. Function undo in MATLAB. Then you will pass your time parameters, initial time, you see that, and final time. Now, your initial time and final time vector, according to the model, is assumed to be what? Horizontal vector. I mean, row vector. But your initial condition for population, it's what? Column vector, which is right here. Okay, that is it. Now I want to suppress the output, so I have to put semicolon. Semicolon to suppress output on the screen. Okay, so this line is going to call the solver. Now this ODE45 is a built-in numerical solver in MATLAB. Okay, ODE45, and that is that. And then I have the solution in line 7. Then I can plot. I'm going to be getting 3 graphs. I can plot the first figure, figure 1, plots the time against y. Now my y, it's going to be two columns, y1 and y2. So when I plot that line 9, that graph, I'm going to have 2 graphs, 2 line plots. Okay, line width, let me call it 3. And this is called face portraits, or you call it integral curves. Integral curves. Okay, and the title of my graph is what? Predator versus prey populations over time. Okay, that is the title of the plot, and the x label is, of course, time. You can use in MATLAB you can use a semicolon or single colon. I mean single quote or double quote. Okay, and then your y label, it's, of course, let me use single quote here. It's the same thing. Is the population. Okay, see, I have my label complete. X label, Y label, X axis, Y axis, or you call it horizontal axis. Okay, let me put comment there. Label for horizontal axis, and this one horizontal, and of course this is label for vertical axis. Vertical axis, you have that, and I can describe a hard description to the figure, to the plot, by calling a legend function. And legend function, I have pray, okay, predator, and location. Location in MATLAB. Now, what I'm doing here, this one here, you can put any name you want on it, but this location, you have to type it verbatim the way you have it here. Once again, see this X label is a function in programming. X label, you have to type it verbatim. This title, you have to type it verbatim. All this, they are function. Even legend is a function, and it's accepting some parameters. But in the legend function, this location parameters must be typed verbatim. And that is telling you where you want to add the description in the plot. So let me put the description. Let me tell the compiler to put the description in the best place possible, depending on the nature of the graph. Okay, that is the first one. If I run this now, if it's, see what I've got. I've got make it let me call this the OD model below. Okay, let me solve that and see what I have. See what I have. This is great and fantastic. As you can see here, the blue one is the prey population, and the red one, or maybe wine color, thick wine color, is the predator. I think I must have made a mistake. I need to swap it around. Predator should be, let me see what I've got. Okay. Y1 is, okay, the prey is the first one. No? What am I saying? Okay, prey is the first one. Predator is the second one. Okay, predator. Let me see. What's wrong here? Yeah, predator is Y2. That's right. And okay, I think I need to swap. Them. So predator prey. Okay. Yeah. So we got predator to be the blue one, and the prey to be the what? The red one. As you can see, over time, the population of the predator will keep increasing See, keep increasing due to interaction, eating up the rabbit. For instance, foxes are the blue lines, okay, while the red is what? The rabbit. Okay, let me add more plots. Let me grab this figure 1 and call that figure 2. Call that figure 2. And then I'm going to plot. Now, this time around, you know what I did here? I plotted the population against time. This is a time, right? And that is called face portrait, right? So pop versus time, right? That's what I did. Population versus time. But this time around, I'm going to be plotting population versus population. Okay? Pop versus pop. I.e., Y1 versus Y2. And that is called face plane in modeling. Face plane. Face plane number 1. Okay? So let me plot the first component of Y. Now, this is how to extract the first component. And if you want to extract the second component, you do that. And then the color is blue. No. And tell me that. The color is blue. And the line width. The line width is 3. You can make it 10. If you make it 10, it's going to be very thick. So you can make it 1. 1, 2, 3 are the 2 and 3 are the most common one. T is going to be more thicker than 1. That's line width. Okay, and I'm going to tie to that. Let me grab this X label. Okay. I don't need that. Let me get this X label and then change the content. So the title is what? Face play. That title is going to be face plane 1. Face plane plots 1. Okay, time is right. No, we don't even need time here. We don't need X label is going to be pre-population. Pre-population. Okay, and Y label is predator population. Okay, and then I can do the same thing for Y2 first, followed by Y1. Okay, and I'm going to call that figure 3. Change this to what? 2, and this to what? 1, and then call this face plane 2, and then swap. I'll call this predator, and then I'll call this prey. Okay, let's see what we have. So once again, look at the nice code. I modularized my code. I separated the ODE function and away from the color function, and inside the ODE model. Inside the ODE model, I use the function undo here. This line is very important. Now let me solve it. Wow, I got a solution. Let me clean everything and do it again. So see what we have. We have 3 plots. Let me make it smaller. Okay, let's make it smaller. shape, and then this is going to be smaller too, just to explain everything. Right, come on. And then I have this. Okay. Why is it frozen? Okay. So I've got all these three plots. Now, I've explained this. The predator is the blue plot. You can click any point on this line to make it interactive. You can click any point here. Right? You can click any point here. You can get... Now, the point here, X is 24 points. Is a time, because in the figure 1 here, the figure 1 is a plotting population against time. So this X is actually representing time variable. So at time point 24.8896, the population of the predator is 58.4758. The same thing goes for what? Prey, right? So this is what a face portraits or integral curves, plotting the population against time. Remember, when you solve the ODE, you have your Y, which has two components, Y1 and Y2. So the Y1 is the blue line, and the red line, Y2 is the red line. So Y against T. So if your solution, for instance, is 3 components, you're going to have 3 lines on the figure 1. Now, I set aside time variable, and I plotted Y1 against Y2, and I plotted Y2 against Y1, and that gave me what? A kind of circular figure. So that is a circular relationship between the population of, say, rabbits and foxes. The same thing for both of them. So that is the end of this video. You can do the same thing for modeling larger systems, even something similar to partial differential equation. Now let me know your comments. Just click subscribe to this channel if you want more of this video, and let me know your comment, any suggestion for improvement. And if you need research consulting with me or collaboration, you can comment in the comment section and send me your email. I will contact you. All right, I hope this is very informative. Thank you for listening, and have a wonderful day.